Okay, stoichiometry not being my biggest, strongest suit, I'm not completely sure what's going to happen here. This is, by my calculation, about 750 milliequivalents of hydrochloric acid. So if I calculated that right, I ought to get about 15 to 17 liters of CO2 off of this stuff. I'm expecting it to happen almost immediately. Work. I don't like the way the top is bulging. It's putting out more pressure than I thought it would. Okay, well that was attractive. Okay, well so trial number 1 was a limited success. No, even better. So I'm having a terrible problem with foaming when I try to use this pelletized limestone. Let's try a little experiment here. I'm probably going to have to come up with an alternate technique for this. I think the limestone's got clay in it or something that's causing all that foam when I try to add the acid to it, so it's probably not going to work for me. All right, let's try. I'm having trouble calling either one of those an optimal reaction, but I think I'm still going to go with the bicarbonate. I'll just be a little more careful when I add, because that other one, frankly, that's just disgusting, and I don't want to deal with that. So let's set this up. This is 1 pound, 454 grams of sodium bicarbonate. So that is a monovalent sodium salt, NaHCO3. That's got a molecular weight of 83, which means that what I just put in there is 6 moles worth of sodium bicarbonate. So since each mole should theoretically produce 1 mole of CO2 when reacted with the hydrochloric acid, that should be around 130 liters of CO2 if I do this right. Since this hydrochloric acid is 35% acid, about 85 mLs of acid should be 1 mole of hydrogen ion. So again, I ought to be able to get about 20 liters of gas every time I put 83 mLs of hydrochloric acid into this device. So that's about 100 ml of acid, as noted. It should be worth about 20 liters of CO2. So I'm going to call that a thoroughly acceptable result. I think what I need to do now is fire up my bicycle pump and put that stuff into the canister, the cylinder, and let's see what we get. So this having spent 3 or 4 hours in the freezer, let's go ahead and see what the pressure is. If this is really CO2, it should have dropped several hundred psi, because the CO2 should have liquefied. Oh my goodness, look at that, almost exactly. 505 psi at 0 degrees Celsius, and we're at just about 500. So identity confirmed. I got CO2 here. Let's try one other thing. There's at least theoretically a reasonable amount of liquid CO2 in the bottom of this. So let's just see if we can let some of it out. This will tell us whether or not. Well, that was cool. That was clearly liquid CO2 that immediately became gas. Let me show you my gauge pressure in this tank. So that's up about 900 psi. If this was working according to theory, that shouldn't happen. It shouldn't be able to do that. And I'll show you why. The idea being that CO2 is going to liquefy at standard temperature at about 840 psi. So if you add more CO2 to this tank, the purple, it should just fall into the liquid state, and the pressure should never rise above 850. So whatever I have in there, it's not pure CO2. I realized a few minutes ago that this tube was broken right here, significantly broken. So there's just no doubt at all that I've entrained non-CO2 gases in here, probably mostly nitrogen and oxygen. Our good friend Mr. Boyle of Boyle's Law of Fame will tell us that the pressure that's inside this tank is the additive pressure of whatever mixture of gases is in there, so that each gas generates a partial pressure and the total pressure is the sum of each of those partial pressures. So because oxygen and nitrogen won't liquefy in the cylinder, what you have is essentially a puddle of liquid CO2 and a mixture of CO2, nitrogen, and oxygen above in the cylinder. So if I turn this thing upside down, gravity will push the CO2 to the bottom, or to the valve, and when I open the valve, I will spray liquid CO2 out. We actually saw that in my last video. If I turn it upright and I open this, what I should do is expel preferentially the nitrogen and oxygen, and the CO2 will evaporate to fill up the cylinder. So I'm going to go ahead and keep pumping until the pressure goes up above 1,000, and then I'm going to just gently burp this thing, and at least in theory, as I burp it quietly, the pressure should drop to around 850, and then it should stop dropping because the liquid CO2 in the cylinder will start to boil and produce more CO2, and I should have essentially a pure CO2 environment in the cylinder. That's what I'm going to try to do. Well, I got a great big duh for you. I figured out the reason. It's again because CO2 doesn't act like regular gases, because it condenses and then boils inside the cylinder, and it turns out that the vapor pressure of CO2 is 840 at room temperature, 20 degrees C, but it's 31 degrees Celsius out here because it's hot. And the vapor pressure of CO2 at 31 degrees Celsius is 1,065 psi. So it's not, or it may have been some contaminating gases, but it's certainly not just contaminating gases. It's going to go over 1,000 psi as long as it's hot out here. Conversely, if I put it in the freezer, the pressure will drop dramatically. My freezer is at minus 13 degrees C, in which case this cylinder's pressure should read 330 psi. So I'm going to put it in the freezer and we'll see what we get. So let's just take a quick look at what we're talking about here. This is the famous ideal gas equation, PV equals nRT. The product of the pressure and the volume is equal to the number of moles times the constant times the temperature. So in this particular case, we're not changing the constant, we're not changing the number of moles, and we're not changing the volume. All we're doing is changing the temperature in degrees Kelvin. And so in this case, the pressure, the change in the pressure will be proportional to the change in the temperature. The degrees of temperature change that we're going to see, 260, that would be minus 13 C, and 304 is 31 C, so that's 0.85. The starting pressure in the cylinder was 980 times 0.85, so we should come out at 838 psi. So if this was compressed nitrogen, when I pull that thing out of the fridge, it should read 838, but because it's CO2, it's not going to act like an ideal gas, and the pressure should be much, much lower. If I do get to minus 13, I should come up with a pressure of 330 psi. So if we pull the thing out of the fridge or out of the freezer, and it's way, way, way lower than 838, that'll be a proof positive that what we have is CO2. And so here's going to be the proof shot. This thing is not at minus 13C, it's at minus 16C. So we should be coming in at about 311 psi. My gauge is unhappy at being so cold, it might take a minute. And there we are, the pressure stabilized and it's at just over 300 psi. So it's all CO2, which makes me regret even more the waste of the 50 grams of CO2 that I blew out earlier when I was trying to diagnose my overpressure syndrome. So as another example, this is oxygen. This is something that conforms very well to the ideal gas law within any pressures and temperatures that I can obtain. So right there, if you look, we've got, come on, focus, 510 psi. I'm going to put it in the freezer, and my prediction is that I'm going to get 428.5 psi. So I've cooled this down to the 16 below 0 C in the freezer, and I calculated we'd come out, what, somewhere around 428, 430. Let's see what we get. This was using ideal gas, and I'm seeing, looks like 430 to me, maybe 440. So here's the problem. I've been expecting CO2 to behave like an ideal gas, and we all have sort of a natural inclination about how ideal gases behave, or maybe we just have experience. And so I assumed that the pressure in the cylinder was going to change with temperature the way an ideal gas would, and it didn't. And we'll take a quick look at why that would be different. And that's why I've been messing around with all these problems with overpressure when really it was all just about the temperature. So in order to understand what's going on here, we have to look at something called a phase diagram, which describes how gases behave under different temperatures and pressures. So long here is the temperature on the x-axis, the pressure on the y-axis. And essentially what you have is you have an area of high pressure, low temperature where the gas is in a solid phase. You have relatively higher temperature and lower pressure where the gas is in a gaseous phase. And you have sort of a central sort of higher pressure, lower temperature range where it's in a liquid phase. And there's this thing called the triple point, which is the pressure and temperature where just minor shifts will either make you solid, gaseous, or liquid. The last one to point out to you is this thing called the critical point, which is where the temperature and pressure are so high that there's kind of no difference between the liquid phase and the gaseous phase, and there's no interface between them, and this supercritical fluid acts as kind of a combination of a gas and a liquid. So let's look at this in terms of nitrogen. Nitrogen's triple point is at 63 Kelvin. That's about minus 210 Celsius, so obviously pretty cold. And at 1 atmosphere, solid nitrogen will turn to liquid nitrogen at about 63.2 Kelvin, which again is minus 210 Celsius. And liquid nitrogen will turn to gaseous nitrogen at 77 Kelvin, which again is not high. It's 273 minus 77, 196-ish, something in that range, negative 196 C. So we're way over here, and we're usually dealing with only gaseous nitrogen, which means that as the temperature goes up, the pressure goes up according to the ideal gas law. So where things start getting tricky is when you're dealing with something like CO2, because CO2's triple point is minus 56.4 degrees C at 5 atmospheres. So that's really not that far off. At 25 degrees C, you've got a gas-liquid interface at only 67 bar. And remember, at 20 degrees C, you're down at about 53.5 bar. When you get above 31.1 C, you get to what's called the critical point, and we've done that in those in that cylinder because we've gone above 31 degrees C. We've gone above 73.7 atmospheres, which is around 1100 psi. So we've been into the supercritical fluid area on this venture, if you will, and at least in theory, if you cool this thing down, the heat that is required in order to vaporize this liquid will shoot you down temperature-wise from the liquid into the solid phase and produce dry ice, which is what we've been doing, and that's the point of this whole thing all along. So the difference between CO2 and the other gases is that in the other gases we're way up here and we're dealing in changes in temperature that produce changes in pressure kind of on an ideal gas law, whereas with CO2 we're seeing phase changes during those temperature changes, so you can't just assume that the pressure inside the cylinder is going to change kind of proportionately to the change in temperature of the cylinder. So it's just a really different situation. I think we've come to the moment of truth. This is 211 grams of CO2. I just don't seem like I can really break the 200 gram mark. Last time I cooled this thing down because I thought that would make more liquid CO2 and therefore I'd get more conversion to dry ice. But according to some gas supplier website, it appears that you get more dry ice if you have this stuff at a temperature greater than 90 degrees, which is 32 Celsius, and a pressure greater than 1100. So I put this thing out in the sun and its temperature is presently 40 degrees C, which means that it's got a pretty high pressure. If you look at that phase diagram, you know that means that this thing is filled with supercritical CO2, not liquid CO2. So let's hook it up and give it a rip. I did put my horn in the fridge, really the freezer, because I didn't see any reason to waste all that heat trying to cool off my equipment. One of the things that I'd like to point out is that this thing's packing at least twice as much pressure as it did in my last demo, and so I expect it to be consequently somewhat more violent than the last demo, which is why I'm going to be wearing face protection this time. I've also weighed the bag because I'd like to see if I can get a yield. So this bag weighs 12 grams, and once we get CO2, or once we get dry ice, if we get dry ice, we'll go ahead and throw the bag back on the scale and see what we get. So no time like the present. Face shield down. I'll give you a 3, 2, 1. 3, 2, 1. Well, that wasn't much. Well, that was a complete and utter dud. Well, you know what? I'm going to call that one an episode and get over all the geeky stuff, and I'll do a quick shot of a yield diagram later, because I'm going to have to spend another week pumping this thing back up. So despite the utter failure, and I have to tell you that frankly a failure to launch at my age is not an uncommon situation, I do want to thank you for watching and ask you to like and subscribe. Tell your friends if you want. If they don't want to watch, you know, that's okay. I mean, look what just happened. And if they do want to watch, I'll be here. Anyway, thanks very much for watching. Have a great day. Crap.